Yeah, welcome back to next session. So here there is another topic we are going to see is MEMS and nano sensors. So it is a completely theory topic and very simple topic we can see here. And to start with, so these are the topics we have completed, and one more topic left out is laser sensors that we are going to see in next session. So if we complete laser sensors, there ends our syllabus. So MEMS, the first one is MEMS, and then in this session itself we shall see what are nano sensors. So MEMS in short, it is known as micro electromechanical systems or miniaturized devices developed as advancements in silicon technology. It is a technique of combining both electrical and mechanical components together as a single chip in a miniaturized form. Miniaturized elements of electromechanical elements are developed by the methods of microfabrication. The overall dimension of a microsystem is within 30 by 30, 30 by 10 into 30 by 10 to the minus 3, in which it includes structures with their features having dimensions of about 100 micrometers. So in terms of micrometers, we can see here. These devices vary from the devices in which there are no moving elements to extremely complex systems with multiple moving elements. These devices are also termed as microsystems technology or micro machine devices. These consist of two major components such as sensing, actuating elements, and signal conditioning element. All along, we have seen signal conditioning wherever the transducers are used. There, we have signal conditioning unit also. We have seen in almost many units in the syllabus. So here the MEMS block diagram. So this is input signal, micro sensing element, signal conditioning element, power supply, transducer, output signal. So this is a simple block diagram of MEMS. So acts as the figure shows how a MEMS sensor acts as a micro sensor. So here you can see the basic components of MEMS, the micro sensors, micro actuators, microstructures, microelectronics. These are all the basic components of MEMS. The advantages of MEMS due to its miniaturized nature, smaller size, low power consumption, sensitivity to input variations, inexpensive, possibility of mass production, less invasive than conventional devices. So these are the major advantages of MEMS systems. So materials used for MEMS, the following materials are used in manufacturing of MEMS sensors. One is silicon, gallium arsenide, polymers, metals, ceramics. So these are the basic materials. Apart from this, we have other materials also. These are the important materials. So here the micro machining of MEMS. The following are the steps to be followed in order to perform micro machining of MEMS sensors: bulk micro machining, surface micro machining, wafer bonding, deep reactive ion etching of silicon, liga process. So all this we are going to see in detail in the coming slides. So the first one, the bulk micro machining. This is the oldest micro machining technique and first used in microelectronics in the year 1960s. This technique involves the selective removal of material from the silicon substrate to develop the miniaturized mechanical components. So the selective removal of material, some material from a component can be removed. To perform this operation, chemical etching is preferred since it can provide a high etch rate and good selectivity. For good etch rate and selectivity, it is possible to do modification in chemical composition of the solution to be used for etching, change in temperature condition of the etch solution, modification in composition of the uh, dopant, and modification in position of substrate which is to be exposed to the etch solution. So this is the bulk micro machining. It is a simple and oldest technique. So the next process is surface micro machining. Initially, to do etching, masking materials is placed on the substrate as shown in figure that I will show you next slide. Most preferable masking material is silicon dioxide. When ethylene diamine pyrocathanol is an etchant or silicon nitride Si3N2 higher etch rate than the other, it is more preferably used. So on the base structure, substrate, the deposition of thin material such as oxide layer to perform as a temporary mechanical layer is made, from which the actual layers are further built. Next, patterning of oxide layer is to be carried out. Since this oxide layer is a temporary layer, it is also said to be sacrificial layer. So that is a removable layer later. Next, a thin film layer such as polysilicon is deposited as patterned. Now this is said to be a structural mechanical layer, and after this temporary sacrificial layer is removed, and now the polysilicon layer is free to act as a cantilever. The process of surface micro machining is shown in next slide. So surface micromachining, you can see here, this is oxide, and this is the polysilicon, and this becomes the cantilever. So this is the silicons on silicon substrate. So this is how the surface micromachining is done. So next step is wafer bonding. Wafer bonding is similar to that of process of welding in large scale to provide joining of two or more number of wafers together to design multi-wafer stack. For effective wafer bonding, it is designed to have substrate of flat, smooth and clean type. So there are three types of wafer bonding. One is the first one is direct fusion wafer bonding. This method of wafer bonding is preferred when it is required to join two silicon wafers together, or alternatively to join one silicon wafer to another silicon wafer that has been oxidized. For example, it is decided to join a bare silicon onto a thin film of silicon nitride. Direct fusion wafer bonding can be preferred. So this method can also be used to fabricate silicon on insulator in wafers having layers of thickness of about several microns. It is very small size. There it is employable. So next one is the anodic bonding. In anodic bonding method, a silicon wafer is bonded on a Pyrex 7740 wafer. So it is using suitable electric supply and high temperature condition. So here these are two wafers can be pre-processed before the process of bonding can then be aligned suitably. Since Pyrex 7740 wafer has a thermal expansion characteristic coefficient nearly equal to silicon, there will be a low residual stress in the layers. Wafer bonding using intermediate layer. So this is whenever it is necessary to perform the wafer bonding at low temperature, an intermediate layer can be used. So for low temperature applications, an intermediate layer can be used. This process consists of the bonding of silicon substrate to another silicon substrate using an intermediate layer of gold material on the surface of any one of the silicon wafer. Since the diffusion of gold into silicon is rapidly done at high temperatures through, and this process is more preferred. So this is the most preferred process. So even though there is a significant increase in etching rate, a depth of etched channel can be achieved with respect to the use of plasma. The etched walls in the channels remain at wide angle theta to its depth as shown in figure. It is very critical to in many MEMS structures. So this is the etched cavity shown here. This is a simple diagram of etched cavity. So next is deep reactive ion etching of silicon. It is in short it is known as DRIE. Deep reactive ion etching of silicon is used to overcome the above noticed issues and the problems that is in earlier processes. This process consists of a high density plasma source to alternatively etch the silicon and deposition of etching protective material on the sidewalls. The dry process is shown in figure. So here this is the dry etched substrate, and the ions, positive and negative ions are reactive neutrals. Reactive neutrals are acting on the surfaces, and this become mask. This become mask, and the ions are acting like this. This process, the polymer layer is deposited on the side walls as well as on the bottom. The polymer layers, bottom of the edge cavity for protection purpose. The anisotrophy of the edge removes the polymer layer at the bottom of the portion of the cavity in a faster manner than at the side walls. The rate of etching in this case is ranging from 1 to 4 microns per minute. So this is the dry process. So the next one, the Liga process. The Liga process is another important process in MEMS manufacturing. The Liga, it is a German acronym of lithographic galvanoforming. It is electroforming, and it is art form. It is molding. It is a German word. It's basically a non-silicon based technology. The fabrication steps involved in Liga process is shown in this figure, and this is X-ray lithography. From here, the photoresist with desired patterns of process of electroplating, and this electroplating is derived as metal product and metal molds, and from here the plastic produced by injection molding. So this is how Liga process works, and the Liga process, the desired patterns are set on a thick film of photoresist by means of X-ray lithography. Because of the shorter wavelength, a higher penetration power into the photoresist materials, X-rays are preferred as light source in the Liga process. Microelectro machines, so those steps are explained here. To provide high resolution in lithography and a higher rate of depth, high penetration power is required. Major steps involved in Liga process are explained. It is decided to develop micro-thin walled metal tube which of square shaped. So it is square shaped, and initially a thick film of photoresist material is deposited on the surface of the SI substrate. So silicon substrate. Most common photoresist material used in Liga process is polymethyl acrylate, that is PMMA. It is very sensitive to X-ray lithography. The suitable thin mask can be used on the on the on the top of the deposition of the photosensors materials on the substrate. The preferable mask is silicon nitride Si3N2, the thickness ranging from 1 micrometer to 1.5 micrometer. So since the masks are transparent to X-rays, a thin film of gold is applied to the area that will block the transmission of X-rays. So gold is will stop the X-ray passing through it. So here development of resist after lithography by the process deep X-ray lithography. The exposed area shown in figure is to be dissolved in the successive development of resist material, and this is electroplating process. PMMA photoresist will have an outline of desired product as shown in figure. Now the process of electroplating is carried out with a desired metal such as nickel to produce the required tubular product as shown. So this is the tubular product produced, and this is done with the plated material layers, metal layers. So this is how it is done. And next step, direct product after resist removal. So after removal of photoresist material By suitable etching methods, the tubular product as per the requirement is produced. So this is the tubular product produced in this process. So that is about MEMS and how MEMS are manufactured and what are the MEMS manufacturing processes are involved. We have discussed here. And next we will move to nanosensors. So nanosensors are used to sense the biological, chemical or any physical information which are to be conveyed as nanoparticles to the macroscopic world. They are much useful in nanoscale range. They have the potential to identify particular cell or parts of the body which is to be observed. They can identify the changes in certain cells in case of diagnosing cancerous condition based on the change in volume, concentration, pressure, temperature, velocity, magnetic forces, etc. This will be helpful for drug delivery and monitoring of different stages of diseases at specific part of the body. It is also possible to detect the changes happened outside body and to transfer these variations via nanorobots which are inserted into the body. So advantages of nanosensors are smaller in size, minimum power consumption, maximum sensitivity, maximum specificity, self-diagnostics, reliability, easy mobility. So these are all advantages of nanosensors. So here the methods of manufacturing of nanosensors. In order to manufacture the nanosensors, there are popular methods such as top-down lithography, bottom-up assembly, and modular self-assembly. These are the three popular methods. First one is top-down lithography. By this top-down lithography method, most of the integrated circuits ICs can be made and hence is preferred to manufacture the nanosensors. This process started with a larger block of material to be processed and etching process is to be followed to obtain the desired form. Further, these etched out components can be used to develop micro level sensors and nano level sensors. In top-down lithography, there are three steps to be followed such as pattern design by generation of mask, pattern making by the method of exposure and pattern transfer by etching off. So silicon substrate is taken as base on which P plus silicon layer is formed as making layer and etching is followed to get the desired pattern. A SiO2 layer is developed over the pattern made in step this one. So in next step. So this is a pattern designed by mask and this is the pattern making. So these are the patterns and we can see the next step. The next, a thick poly silicon layer is deposited over the SiO2 layer as shown in this figure. So then the various pores exist are to be created by means of using etching method, preferably by plasma etching method. Finally, the developed pores are to be opened by means of applying hydrofluoric acid, which removes the sacrifice layer. It is shown in figure. The sacrifice layer is removed at any point of time in the process. So the deposition of polysilicon layer and development of pores are shown in these two diagrams. So next method is bottom-up approach. So here you can see the approach involves the assembling of components such as molecules and atoms and placing them in one in order to get the desired sensor. It consists of movement of atoms of a particular substance one by one with respect to their corresponding positions to obtain the desired form. This position will preferably be used to develop starter molecules of self-assembling and assembling the sensors. It is a very difficult method to use, especially in mass production. So, in case of smaller number of products, this can be used, but in case of mass production, it is not a suitable method. So next one is molecular self-assembly. By this method, the molecules adopt a defined arrangement without getting guidance or support from an outside source. In this method, a piece of previously developed or naturally created nanostructure can be considered as the base. Then this nanostructure is immersed in free atoms of its own kind. Initially, the structure would begin to have a shape with an irregular surface. Further, it would cause the nanostructure to become more prone to attract more molecules. It continues the pattern of capturing more number of free atoms, and a larger component of the nanosensor is then obtained by assembling more of itself. So next is advantages of development of nanostructures. By this molecular self-assembly of biological elements is that they will degrade back into smaller individual molecules which can be broken down by the body. So applications of nanosensors are nanowires, carbon nanotubes, blue crab nanosensor, electrometer, chemical sensor, military and security applications. So these are all the applications of nanosensors, and in future we are going to have more number of nanosensors across almost all instruments and gadgets. So that is about nanosensors and MEMS. In next class, we will see the laser sensor, and there is the syllabus. So we stop here. So these are the books and references. We stop here. Thank you, students. We will meet in next session. Thank you, students.